Hello and welcome to another episode of the Women Developer Academy Speaker Series. Today we are going to be joined by Philomena Mbura all the way from Nairobi, Kenya, as she talks about exploring the depths of deep learning. So if you are a machine learning enthusiast, if you want to know more about deep learning, I believe you have tuned in for the right session. Now, for the past few weeks, we have had amazing Women Tech Makers ambassadors covering various topics. And so I will hand it over to her to just walk us through the topic that she selected. Over to you, Philomena.
Thanks, Alela. So hey everyone, my name is Philomena. As she said, I'll be walking you through exploring the depths of deep learning and AI. So a little bit about myself. I'm a data scientist at Hello Tractor, and I also lead the Women in Data community, and I'm a WTM ambassador. So let's start. Yeah, so I'll start with the definition of deep learning, but before I get to that, I'd like to start with where actually deep learning stems from. And it's like a hierarchy where artificial intelligence is at the top, then machine learning, then deep learning is right at the middle. So for artificial intelligence is just the sense where we enable machines to be able to mimic human behavior. I think it's all the rage right now where everybody is just talking about AI. If you watch Google I/O, it was all about AI. And so I think this is part of AI. But between artificial intelligence and machine learning, we have another layer called machine learning. So machine learning is whereby we enable machines, or it's rather a branch of artificial intelligence whereby we enable machines to be able to learn from the data and be able to make decisions based off of the data that we have fed into it, in a way that is not explicitly programmed, such that you don't explicitly tell it to do this. It learns from the data and it's able to make a decision. So deep learning, which is what we're going to discuss today, is a subset now of machine learning. So it's inspired by the architecture of the human brain, such that it uses things we call neurons. Same way we have neurons in our body, which are used to send signals and messages to the rest of our body. Now, in this case, neural networks are used to be able to neurons are the building blocks of our neural networks, such that if you have one layer, it's just a neural network. If you have more than one layer, it becomes a deep learning neural network. And we'll be able to delve into that more as we move along. Oops. So let me just hide this. So the popular deep learning frameworks that we have include TensorFlow, PyTorch, and Keras. So for this session, we'll be mostly delving into TensorFlow and Keras in the mini project that we're going to do at the end. But then also in the other sessions or during your own free time, you can be able to explore what PyTorch is and how you can be able to use it for deep learning. These are not the only three that we have, but then I consider them the main three, and I thought it'd be a worthwhile mention for this session. So one question that I've been asked before when doing a session on deep learning is what's the difference between machine learning and deep learning. So I thought that it would be wise for this session to be able to just expound very briefly on the differences between the two. So the main difference that I would say between machine learning and deep learning is that for machine learning, you are able to explicitly define the features that you have in your data. So you can be able to do manual feature engineering so that you can be able to inform your decisions. But for deep learning is you are required to feed your data into your model, and then now your model is able to automatically learn and generate features from your data, so that you don't necessarily need to do any much manual feature engineering. So just by the definition of deep learning, as you can, if your model is learning from a data by learning by itself without you explicitly defining, by its own definition, it means that you require a large amount of data, which in comparison to machine learning, where you may require just moderate amount of data. This also means that in deep learning, you will need to have very high computational power for you to be able to get your neural network to work, and just so that it may be able to learn from your data and give you the output that you require. Also, deep learning has been all these frameworks that we have, and therefore you may find that when you are building your neural network, it becomes some sort of black box where you don't necessarily know which feature is being used in your neural network or what is being prioritized and such and such, but there are ways to go about that to be able to understand your neural network more. But by definition, it is sort of like a black box, whereas now in machine learning, it's more interpretable and you have a clear understanding of how your decisions are made, because more often than not, you're the one who's actually telling your model, like, this is what you should prioritize when you carry out all your EDA and the likes, and you're able to know that this is a feature that is being utilized more and such and such. So understanding the basics of neural networks. So what is a neuron? So in this context of neural networks and machine learning, so it's the fundamental building blocks of everything that we do within neural networks. So I'll just give you a brief overview of what's going on here. I try to simplify it as much as possible with this image. So what we're doing here is we're feeding in this triangle into our neural network, and we're trying to tell it to be able to predict whether it is a circle or it is a triangle at the end. So the X and the Y here, for the X, it represents no, let me take a step back. So you will have, for when you have an image, it's basically built by the pixels. So here X will be the number of times it is divided by horizontal lines, which I have not drawn here, but you can imagine there are horizontal lines, and then Y, the vertical lines. So they intersect to form little small black boxes, which are in this case going to be represented by the Z. So when you do a multiplication of X and Y, you get the number of pixels that you have in this picture or in this triangle that we have here. And then now that is what you feed into the model. So Z, which if you had X as 28 and you had Y as 28, then the number of inputs that you will have for this particular neural network will be Z. So it's X times Y. So this will be represented by this here. It will be fed into the neural network as the input layer. And then we have the middle layers, which are the hidden layers. And then we have the outer layer, which is the output layer. So when it is fed, those the very small pixels that you're feeding into your neural network, they usually are represented by a value of the pixel. And now when you have that value of the pixel, you have to multiply it by something we call the weight. And each of these will have its individual value. And then each of these lines that we have here, which is connecting to the next layer of the neural network, has also another value, which is now referred to as the weight. So neural networks work by matrix multiplication, whereby you have this value that you have here, you multiply by the weight, and then the value you have here, multiplied by the weight. Then it all comes together here by the way you do a matrix multiplication, horizontal times vertical. And then you have the summation that you have there, and then you add something we call the bias. So the bias is supposed to give you how high the weighted sum needs to be before passing through the activation function. And so now the activation function is what determines whether a neuron will be activated or not once it gets to it. So all these neurons that you have here will go through the same process which I've outlined here, the matrix multiplication, you add a bias to it, and then you pass it through an activation function to determine whether it's going to move to the next step or not. So by the time it gets here, for example, and then it says that it is a circle, whereas it's not a circle, then now there's an error that is attached to it during the training. And therefore, your network is able to say that you said that this is a circle, but then in fact, this is supposed to be a triangle because we can already see the output from the training data. And so it now goes back through the layers saying that it was a wrong inference, and therefore we need to go and adjust the weights and the biases that we have so that we can be able to iterate it again and come back and repeat the same process again until we're able to get to the value that we want, which is now a triangle. So that's what we call the backward and the forward propagation, that iteration where it goes like round until you get to the right answer, which is usually defined in your code as you're writing down the code. So like I said, we have how the neural networks work and learns from the data is through the backward propagation. So back propagation is a method used to calculate the gradient of the loss function with respect to each rate by applying the chain rule. So like I said, it's an algorithm that's used during training that calculates the error of the network output and distributes it back to the layers, adjusting the weights and the biases accordingly. So there are three main things that are important in this process throughout all the layers. It's the weighted sum that you have that's influenced by the weights when you are adjusting, the activation function that influences whether the neuron is going to be activated or not, and then you have the output, whether it's going to be, if you have gotten the right output from your data. So we have different types of activation functions, which determine whether your neuron is going to be activated or not. I'll just briefly go through a few of them and not all of them, depending on the ones that I deem that have been used more often. So we have the binary step function, which is usually for binary instances, and it's used mostly in the last layer, which is called the dense layer. But it's not often used because it's a bit too simplified, and therefore people often choose to use other activation functions when you are doing like a binary search. We have the ReLU. So the ReLU, if the input is negative, it outputs a 0, and if the input is more than 0, or rather a positive, then it gives you the actual value. So the difference between the leaky ReLU and the ReLU is that the leaky ReLU is more advanced in that it's able to also apply a normalization or a scaling factor to the negative values, whereby when you have a neuron that's not being activated as should, then now, and your ReLU is not working properly, then it's best to switch to a leaky ReLU, which is able to now, it's a little bit more advanced and may give you better values. You have the tan H, which gives you values between -1 and a +1. We have the softmax, which is in the last layer, and it's used for a multi-class classification problem, and the sigmoid, which is used for a binary classification model. So I had highlighted the sigmoid and the ReLU here. Like I said, the sigmoid is used for binary, and the ReLU is by definition what I have highlighted before. So I'll give you an overview of TensorFlow and Keras. So TensorFlow is an open source machine learning framework that is supposed to make your machine learning and your deep learning process of coming up with it a bit more easier. And Keras now is a high level API that is built on top of TensorFlow that's supposed to simplify the process of you building your neural network. And so more often than not, you'll find yourself using Keras if you're doing any deep learning neural network. So building a simple model. So when you're building a neural network, it's a bit different from when you're doing just the conventional machine learning problem. So for the conventional machine learning problem, you'll find most of your time is spent through cleaning the data and EDA. But for a neural network, you'll find that most of your time is spent through gaining the right type of data, because you require a very representative data set for you to be able to actually get the right predictions from your data. So you'll start with the problem farming, which is around 20% of your time. You have the collection of the data sets that you need to be very representative, which takes around 30% of your time. Designing your model, which more often than not does not take a lot of time because it has been simplified through the frameworks such as Keras and TensorFlow. Then you have your evaluation and your testing, and the testing also takes a significantly more amount of time, because now you need to actually verify that your data is giving the right output. So here I just put in examples of how you can be able to map out what we have in machine learning to what we have in deep learning. So when you're doing a linear regression, and if you'd like to achieve the same output as a linear regression, then you can use this fast sequential neural network with a dense layer and an activation as none. If you're doing a logistic regression where you are doing a classification problem of an either or, then you can use a sigmoid as your activation function, and of course you'll use the same as the previous one for linear regression. If you have just one layer in your neural network, that is, in this case, we just have one hidden layer, which is the one using ReLU. And then we have this final layer here, which is the dense and the output layer. So it's not really considered as a layer in this case. So this is just a neural network, but then if you have more than one layer is when you have a deep learning neural network, which is what we have here. Yeah. So let's talk about the dense layer. So regardless of your type of network, your object layer will almost always be like a dense layer. So it's very dependent on what you have. If you have your classification problem, it's more or less similar to what we're talking about. Same way your activation function is the same way your activation function determines the output that you want. If you want a binary classification, if you want a regression, if you want, depending on what you want, then that is what you'll specify as your dense layer so that you can be able to specify the number of outputs that you want and the diversity of the outputs that you want, for lack of a better word. Yeah, so training and evaluating a neural network. So this is just an example, a very minimal example that I've come up with. I'm using the MINS data set just to be able to give you an understanding of how the neural networks work. So of course you start by splitting your data. I have not included the other parts where you're loading your data and the rest because that goes without saying. But you start by splitting your data X train, Y train, X test, and Y test. The second step is normalizing your data. Of course, you want your data to be normal such that it does not introduce bias to what you're trying to achieve. And of course, it's going to improve your performance of your data. You can try working on your data without scaling it, and then you work with scaling. And now you can be able to see how much of a difference it plays in how your output actually looks like and how accurate it is at the very end. So of course, at first we flatten what we have because we want to be able to input it in the input layer, and then we use the ReLU activation in our first layer and with an input of 128. So the 128 is the number of neurons that we have in our input layer, in our hidden layer, in our first hidden layer. And then the second hidden layer also has 128. And we're also using ReLU as activation. And then our last layer, which has the value of 10. So 10 is the number of outputs that we expect from our data. So the MINS data set has values ranging from 0 up to 9. So that gives you 10. And so what we're trying to achieve with our problem here is we have a data set that has multiple numbers varying from 0 to 9. And we want to be able to say when you pass in a value, you're able to say this is a 7, regardless of how it's written. If it's a 7 that has the stroke in the middle of it, it's just a normal 7. So the diversity of the data set is what determines how accurate this is going to be and the output you're going to get. And so we put the value there as 10 because we expect 10 outputs from it. Then we have where you compile the model. So the optimizer argument specifies the optimization algorithm that you use to update the model's weights during the training. And here, when we're fitting the model, we have your X chain and your Y chain, so such that you've already trained your data set before. And now, so you're training your data set right now. You've specified your epochs as 3. That is the number of times it's going to iterate through the whole process again. As you can see, you want your loss to continue decreasing as you increase the number of epochs, and you want your accuracy to continue increasing as you increase the number of epochs. So as you can see, when we started, your loss was at 0.2 and the accuracy was at 0.91. But at the last iteration, it has significantly reduced your loss to 0.08 and your accuracy is at 0.97, which is pretty good. And so the problem that we need to try to mitigate or prevent from happening is that we don't want our neural network to learn explicitly from the data in that it masters what our data looks like, such that when you expose it to a different data set, it's not able to give you the right performance, or it now does not perform as well as it was performing within the training. So now you use your test data set to be able to see whether your your neural network is performing as well as you'd want it to. So I passed it through this, and now we're able to see the loss is at 0.09, which is significantly close to what we had before, and the accuracy is at 0.97, which means that it is actually performing as well as it was performing with the training. And what you're trying to prevent is a significant difference between your last epoch here and your in your test data set when you're testing. If it's a very huge difference, then you know that you need to go back and work on your model to see whether you can be able to adjust the parameters so that it is not over relying, and it is not if it is not overfitting your data. Yeah, overfitting or underfitting, either way, it's going to give you a very significant difference. Yeah, so after that, I tested it by printing out from the predictions, the second one. So the first one will be 0, the second one will be 1. So it's a number 2. And then I went ahead to print out how it actually looks in our data set to see if it's actually a number 2. And you can see that it's an actual number 2. And so our model is more or less performing how it's supposed to perform. Yeah, so applications of deep learning in various domains. So we have computer vision, where you have things like image recognition and face recognition. We have NLP. We have healthcare, where you can have things like cancer detection, whereby you train your neural network enough to be able to identify how a cancerous cell should look like and how a normal cell should look like. We have agriculture, where you can have things like crop disease detection. We have security and defense and fraud detection in manufacturing and retail and e-commerce, in things like inventory control, which is largely used even nowadays. So I took the time to bring in insights into various types of neural network architectures and the applications. So deep learning is not a one size fits all approach. So you don't just use one network to across all of them to represent whatever you want to achieve. So you need to be able to understand your problem, whether it's an image classification problem or it's an image generation problem, or it's a clustering problem. So I've just listed them out. I won't go through them one by one, but maybe you can refer back and see where you can be able to apply whatever you would like to approach with your problem statement. Yeah. So awareness of ethical considerations. So by definition, I think it goes without saying, AI, it's been the talk about ethical AI and how you can be able to do AI for good. So when you are coming up with your neural network, you need to be able to make sure that your data set is very representative of what the real life actually represents. For example, if you are doing facial recognition and your data set is highly representative of maybe the black race or the white race, you need to be able to make sure that it's actually giving the right or the same output for each race. And even if it's the same, it is the right output, to be able to mitigate the cost of having bias in your systems, which can also bring in a lot of problems even back to you and your company, regardless of where you're working from, because it's against the law, in short. So privacy and concerns and security, you need to be able to make sure if your customers are sharing very private data with you, how you're going to handle the data, who it is exposed to, who's getting access to whatever model that you're trying to build, and how you're going to ensure that it is not used against what you've purposely built it for. You need to make sure that it is very transparent. You're able to actually explain what is happening within your network. You're able to be held accountable should there be any risks of using your network or your model that you have built. So you need to, even in the event of any failures, you need to be able to define the ways in which you're going to be able to address the failures that may come with having your product out there. Yeah, so I have a small quote. So TensorFlow and Keras are like the paintbrush and palette of machine learning world. So they equip us with the tools needed to turn raw data into beautiful meaning insights. So I'd encourage you all to maybe go through this recording again and maybe go through some of the blocks of code that we have there. Sit down, go through the different activation functions, go through how you can be able to make your neural network perform better. Start small with things like the means data sets, which is usually like the Halo world of the neural networks world. And you can be able to actually learn and build things that give us a solution to most of the problems that we're encountering here. And the problems that we've mentioned before in the areas which neural networks are used. So for the full code block, you can go through the Colab demo that I have here. It's the short URL, and you can be able to see the short code that was written. And I think I've done 2 of them in that Colab. Yeah, and that is the end of my presentation. I'd like to thank you all for joining. And if you'd like to reach out, you can reach out to me through my LinkedIn or my X, which is at Mbura Philomena, and Philomena Mbura on LinkedIn. Yeah, thank you. Over to
Wow.
you.
Oh, thank you, Philo. Such a lovely, lovely presentation. Benson Kingori is asking if it's possible for him to get the slides after.
Yeah,
Yeah.
sure.
Oh, okay. So I guess we will upload it. You will upload it on your X or I don't know, LinkedIn. Which one do you prefer?
I think I can do LinkedIn.
Okay, so you can check out her LinkedIn, and then there she's going to upload the link, and then you could just gain access to it. Again, if you have questions for Philomena that you would like her to address, kindly drop it on the chat section. She still has a few more minutes, and I'm sure she could be able to take them up. Okay. Any questions for her? Or was it
And
so
you can also
clear
reach
that?
out.
Okay, you're still going to
Can
reach
also
out.
reach out. Yeah.
Okay, great. If you have questions for her, please feel free to reach out to so that she could be able to address it and take it up with you. Since she has already shared her X handle and LinkedIn also. This was very, very amazing. Thank you so much, Philomena. And since we do not have another session scheduled for next week, we will be resuming on October. Please tune in for more. And we're going to be kicking it off with a flatter conversation. But for now, this is goodbye from me. And I guess, Philomena, if you have any parting shot or a place for them to access resources, you could just wrap it up for us.
Mine is just to say thank you for joining the session. I'll share the slides as requested, and also you can also read through my Medium where I've written an in-depth article on an introduction to deep learning. Yeah.
Okay. Thank you. Thank you so much, Philomena. Goodbye from us. Bye, everyone.
Bye-bye.